it is. So this representation, by the way, is very useful whenever we have a quadratic clustering, not only in the context of proving that it's a good clustering. It's a proof vehicle in much of spectral clustering, actually, and occasionally used in other places like k-means and so on, because they are all quadratic functions, as we'll see on the next slide. Okay? So basically, we have a clustering that is represented as a subspace. We see it as a subspace. And here is the k-means cost. As you remember, the k-means cost has many different formulations, and one of them is that the k-means cost is the sum of distances inside clusters. And we are going to use this formulation, and in that case, we can write the k-means cost as the form minus 1/2 x transpose ax, where aij is basically the scalar product of two data points. There is a little catch. We have to also make the mean of the data be 0. So if we make the data 0 mean, then we can represent the k-means cost function as a constant plus this expression that depends on the cluster. Actually, it's interesting that this matrix appears also in support vector machines. It's the gram matrix of the data. So there is a connection between support vector machines and k-means, which again tells us that we can think of support vector clustering, where I didn't go into so much detail. Okay? And then with a little bit of more processing, we can remove the last vector and get a k-means expressed as this subspace basis. So I'm going to write it as y now. Okay. By the way, k-means is not the only cost that is quadratic, and in particular, the normalized cut, the multi-way normalized cut that is used in spectral clustering is also a quadratic cost. And then there are costs. There are other costs used in spectral clustering, like average cut. That is also a quadratic cost in the sense that it has an expression of this form. There is something called correlation clustering, which is also a form of intercluster distance cost, which is also a quadratic cost. So if you look for them carefully, you can find several other instances where the cost is quadratic in the matrix. Now, I want to hear a question. If the cost is quadratic, why is clustering hard? Yes, wouldn't you jump and ask why is that? So if I can put k-means in this nice quadratic form, or this one, why is it so hard to cluster? It's discrete, yes. So just remember, this is I can optimize this for a real value matrix X. So I can optimize this over all subspaces, and that will be an eigenvalue function or a spectral solution. But if I want to optimize it and find a matrix that has zeros and ones, or zeros and non-zeros, then it's a hard problem. It's a combinatorial problem, which we knew all along that k-means was. However, if I for a moment pretend that it's not a combinatorial problem, but a continuous problem, so x or y can be any subspace, then I know how to find the minimum or maximum. Yes. So it was minimization of a quadratic function with a minus sign. So I'm looking for the maximum of this quadratic form, and the maximum of this quadratic form is given by the first k-1 eigenvectors of the matrix A, or in other words, the k-1 principal subspace of the data. So if I do k-means without actually enforcing that the matrix has zeros and ones, I do principal components really. But as I said, and this is a relaxation. Sorry for the typo. Yeah. So this is what's called the relaxation. Instead of impose, I forget about the discreteness constraint, and I get an easier problem. So basically, doing principal components is now shown to be a relaxation of k-means. And as I already told you, the intuition is that it finds the subspace where the clusters lie. But it tells me what points belong to them. However, what we can prove is that in some sense, this discrete matrix is close to the principal components in terms of subspaces. Not in terms of matrices, but in terms of subspaces. They are close. They may have a small angle. Another thing that I get from solving this relaxation is that I get a lower bound on the true cost. So no matter what clustering I have, in particular, the best possible k-means clustering on the data, will have the cost larger than the cost obtained from the relaxation, which is the sum of the first k-1 eigenvalues, which is the minimum of this with our relaxation. Yes? And so I have a good lower bound. If the clustering is good, that's what I'm going to show, that this lower bound is also very good. If the clusters are coincide with a point, so if I have in some sense perfect data to cluster, then this lower bound is tight. I get equality, which means that in general I have the best possible lower bound in some sense here. Yeah. And now the theorem follows. The theorem looks at what's called the integrality gap, the difference between the lower bound, this is here, and the cost of an actual clustering. That's what's on top. And on the bottom is the difference between the next two eigenvalues. This is the eigengap of the matrix. Yeah? So I want to know for a given clustering. Suppose that I found a clustering. I compute its cost. This is it. Or I compute this expression. I compute the best possible cost. And then I normalize by the eigengap. I refer to it by to the eigengap. And if this ratio delta is large, then there is nothing I can say. But if this ratio is small, in particular if it's smaller than this expression, then I know something very important. I know that I have found a good clustering. And it's good in the sense that my clustering delta that I found is no further than the optimal clustering that I don't know than this distance. And this is in the misclassification distance. Okay? So again, the misclassification distance between my clustering and the best possible clustering is no larger than this many points of the data. And how to say, the proof may be long or complicated, but the idea is very simple. This is a good clustering because it's very close to the subspace spanned by the y's is close to the principal subspace. The best clustering is only better than this, so it's also close to the principal subspace, definitely, since it's better than this one. And this eigengap tells me how stable that principal subspace is. Yeah? That's a fundamental result in matrix analysis. If the gap between, so I'm looking at a k-1 principal subspace. If the gap between its smallest eigenvalue and the next eigenvalue is large, it means that that subspace is very stable to perturbation. If I perturb the elements of the matrix by a perturbation of small norm, then the subspace will remain will very little. If the eigengap is 0, it means that the subspace is not even well defined. And if the eigengap is small, then it means that the subspace is very unstable. So I want a matrix that has a stable subspace, and if I find a good clustering on it, then I can guarantee that I can guarantee how good it is with respect to the optimum. And notice, by the way, that epsilon is smaller than 1. OK, epsilon has to be smaller than the smallest cluster size. This is P max is the largest cluster size, so this product is always smaller than the smallest cluster size. So if the theorem holds, it means that I make an error that's guaranteed to be smaller than the smallest cluster. So it means I have found all the clusters. So the intuition is simple. The proof is a linear algebra proof. And the drawback is, of course, that I can't apply it all the time. I have to have found a good clustering first. And it's not guaranteed that any data set contains a good clustering. So the data set has to be clusterable, and I would have to find the clustering. Now, the good news is that if the data set is clusterable, empirically, one can see that actually algorithms do find the optimum, and that they run faster. So there is a lot of evidence that if there are good clusters in the data, an intelligent algorithm with the intelligent initialization, I have to remind you of that always, will find good clustering, and will do it so much faster than if the problem is hard. Okay. On the other hand, there are many cases verified empirically, and it's predictable. This is what's called the worst case result. It means that I have made no assumption whatsoever about the distribution. I only check the conditions of the theorem, and it either applies or it doesn't. So it has to, because I make absolutely no assumption, I don't rule out any cases. It's a worst case result. So there are so many good cases that are not covered. In particular, there could be cases, and there are cases, when the clustering, I find a good clustering, but I can't prove that I found it. So I don't get the certificate of optimality by this theorem. Yeah? On the other hand, if it applies no matter what it was. Okay? Here are some experiments showing how good it is. So these are 3 clusters. 1,000 data points in this case, and they're projected on the principal subspace because there are 3 clusters that has 2 dimensions, so you can visualize them. But if you notice up above the data is actually in 35 dimensions. And the first plot just proves that indeed, if I do principal components, that's what I did. I did principal components on this data set and displayed it. And the principal components does find the relevant subspace. You can see the cluster here, although we are looking at something in 35 dimensions. And the next 3 plots show the bound, calculated for, I don't know if it's the true clustering or the best clustering found by k-means. It doesn't really matter because they are almost the same. And 0.3 is the size of the smallest cluster, and sigma is the standard deviation of the Gaussians. What I show here is the extreme point sigma equals 0.4. This is what you see. So the clusters are separated like this, or more separated because they are more concentrated. Yeah. So they can be very concentrated. And this is the bound, and I plot it until it gets near to 0.3, which means as long as it's relevant, or as long as the theorem applies. So what this says is that for very large separation, it applies with a low bound. But for larger separation, or for less separated clusters, the bound gets looser. The clustering is always almost perfect, right? So the error here is almost 0, always. The bound doesn't know that. It grows a little. And after a point, when these get near each other, it becomes uninformative. I can't apply the theorem anymore. In truth, if I had more clusters, the bound would be weaker. So with 3 clusters, I'm in a better shape. If I had 5 clusters, the bound would be less informative. It's a drawback of being in the worst case. OK, and this is what I had to say about cluster validation. So for some quadratic functions, and I repeat, you can do this for k-means, you can do it for spectral clustering. I don't have the formula on the slide. But for spectral clustering, what you would have here would be the normalized cut. And what you would have here would be the first k eigenvalues, because we have to exclude the first eigenvector, which is non-informative. And the eigengap would be below. So we have a very similar formula for spectral clustering. We can do it in the case of spectral clustering as well. Yeah. And this is what I had to say about cluster validation. On some cases, we have results, proved results. In most cases, we don't. And basically, it's an area of active research. And I must say, related to the previous question about how to compare soft clusterings or how to validate soft clusterings, that's also an area of active research, if you are interested. OK. Now, this is what I'm going to talk about very briefly, or not at all. And feel free to add your own bullets here. I mentioned hierarchical clustering many times. I'm going to say a few words about it now. I mentioned briefly subspace clustering and biclustering. They are related. And partial clustering, too. They are related. I'm going to say a few words about them now, because actually these are things people do, and sometimes there are problems that require that. And so you should know that there is work on it, and that you can think of it of clustering in these terms. And lately, the least I have to say about ensembles, but it's also interesting work, and you should know that it exists. So what's a hierarchical clustering? I guess most of you do know. But basically, it's the picture like the dendrogram I had before, where how to draw it? I first partition the data into 2 clusters, and then I go on and partition these clusters into 2 or more, maybe 3, and then I go on and partition what's left into more clusters. And the picture that people like to draw is the dendrogram. Which shows how the partitioning goes all the way to the level down of at the point level. And often in the dendrogram, you show these heights as the change in cost from one level to the next. There are 2 ways of doing it algorithmically. So what does it mean that it's a hierarchy? It means that any cluster at this level is strictly included in a cluster at a higher level. You can do it top-down, and then it's called divisive or partitional clustering. Or you can do it bottom-up, which is called agglomerative clustering. So in agglomerative clustering, you start from the points, and you merge 2 points together in a cluster, and then you look what else you can merge, and you merge maybe 2 other points. And so the clusters grow by merging. As a particular, so it's typically easier to define an algorithm for agglomerative clustering. For any cost function, practically, you can define a greedy algorithm that does agglomerative clustering. It's a bit harder to find divisive clusterings because you have to look at all partitions, theoretically, to find the best one. And that's hard. And also, the first step is the hardest. So if you get started, then it gets easier. But the first step is hardest. So there is a very special case that's interesting. In spectral clustering, you can do it. Single linkage, because everything is easy. You can always do it. In spectral clustering, you can do it too. And that's done. That was the original spectral clustering algorithm that just split into 2 clusters. And then recursively looked at the at the 2 clusters and split them again. Because there you have 1 eigenvector to use. And there is a very easy algorithm. In fact, it has been, this particular algorithm has been studied in theoretical computer science a lot, splitting into 2. It's called Sparse's cut. So there are various other cuts, like the normalized cut in computer science, that have been studied extensively. And if you want references, I can give you some. And you can use them for partitional clustering. OK? And then for mixture models, people have defined hierarchical versions of mixture models. Hierarchical means that you have a hidden variable for the clustering, and then you have a hidden variable for above. Basically, you have a hidden variable for each level of the clustering. And they have been defined also for Dirichlet process mixtures. So parametric or non-parametric model-based clustering can be defined hierarchically. There is a little catch with these kind of models when you define it hierarchically, though. Because if you think of just think of a very simple situation. Suppose I have a variable z that talks about, that defines this split, 0, 1, and this split. And I have a variable z prime that defines the next split. That can also take values 0, 1. And then here I have my little clusters. And I don't observe this, and I don't observe this, so I have to put distributions over them. Now, when I label these clusters, I have to be careful because I wouldn't know, it's hard to distinguish when I observe nothing, whether this is z equals 0, z prime equals 0, or z equal 1, z prime equal 1, or so. So basically, none of this is observed, and so it's hard to distinguish between. In fact, I don't have two different variables, but I have a variable with 4 states, really. And so if you know graphical models, then it's easy to characterize which situations are identifiable and which are not. This one is not. You'd have to have at least 3 neighbors to have an identifiable situation as a necessary condition. But yes, these models exist. And these models are useful because many people, there are situations when there is actually a hierarchy in the data, typically in biology, where really there are descendants and ancestors, and or there are groups and subgroups of things that naturally occur. So it's good to be able to find them. The word algorithm is a pretty old agglomerative algorithm for k-means, and I'm going to skip it. Exercise, derive it yourselves. You all can do it. What is subspace clustering? This is another problem that was actually suggested by real data and real tasks on real data. For instance, in gene expression data, you get a large matrix of genes and a matrix of conditions or experimental conditions or patients or whatever. So you get genes here and conditions here, and these can refer to, let's say, patients that have been analyzed and what genes have been expressed for this particular patient. And so a natural thing to do is to say, well, these are actually patients with a certain kind of disease, let's say a certain a form of cancer, and how many types of tumors are there? Are there subclasses? Because as you know, cancer is not well understood, and different subclasses can respond to different treatments. So it's important to discover this. However, the problem is that, so you would like to cluster the conditions. However, for each condition, there is only a small set of genes that is actually interesting in that condition. And for another, so let's say these are one type of conditions, and for them, it's this subset of genes that's interesting, and the others are not, and the others vary independently of the condition. And for the other type of tumor, there is actually not the same set of genes, but another set of genes here that's relevant. And they could overlap, or they may not overlap. So I want a clustering on the conditions, but I also want some variable selection on the genes. However, I don't want to. I want to find separate variables for each group. And this has come in different names and different flavors. What I just described is known best as clustering over subsets of attributes, attributes being the genes, because every cluster depends only on a subset of the genes, obviously. If it's called biclustering, then it means that actually I impose these to not overlap. Or I impose maybe something stronger, that I have a clustering on this axis as well. And that's called a biclustering. I want a clustering this way, and I want a clustering this way. And if you have data that supports it, then you can think of multi-way clustering, where you have a data cube, And on every coordinate, the variables cluster, and so on. And people have pushed it even farther. So I call all of this subspace clustering because any subset of attributes is a subspace, defines a subspace in the space of coordinates. But there are other algorithms that are sort of subspace clustering proper or extreme subspace clustering, where actually they look not only at the set of genes, but basically a linear combination of the genes that defines a subspace in this space. And maybe a different one for these. And again, they could overlap or they may not overlap. And they could cover all the features, or they may not cover all the features or all the attributes. This is the problem. Okay. And here are a few of the approaches that, and really only a few because I don't even know all of them. There are many others, and transactions of knowledge and data engineering is the primary place to look for references there. But you can equally well look for references on by the names, because the clustering community is clustered itself. So there is not there is no conference on clustering. So there is no special place to go for literature on clustering. You have to search. You have to hit all the clusters, or at least the one that contains the information you want. Okay. So one fairly publicized paper is called Clustering on Subspace of Attributes, COSA. It's by, comes from, I'm sorry, I have an old version of the PDF. I don't understand how. Okay, so the reference is J. Friedman and Meilă from Stanford. So there are two statisticians. However, this is yet another paper where every little step is done statistically very well. However, this is not a model-based clustering. And it's not estimated by a probabilistic algorithm. It's the best they could do, probably, in the conditions. And what it does is the following. It assumes that the clustering is cost-based. It's a form of k-means. Actually, it's a form of, let's say it's a form of k-means with some normalizations. And they are saying, if I'm doing regular clustering, I'm going to optimize this pseudo k-means cost. But if I want to actually select a subset of variables for each cluster, I'm going to add an entropy term. And so the entropy is maximum when I take all the features into account. If I penalize by the entropy, if I penalize high entropy and I make an entropy, insist that the entropy be low, I'm going to select a small subset of clusters. And there is a regularization parameter that says how much I'm going to insist on low entropy, which means how small these sets I want should be. There is no term that says that these sets should be different or equal. Okay? And so this says find the best small subset for each cluster and find a good clustering in this space. And then what they do is just they alternate. They start with all the features, get some clustering, find what is the best subset that describes each cluster in this clustering, and alternate. And that's it. Actually, this one is a fully probabilistic approach. It says, OK, Dirichlet process mixtures, as you saw them yesterday, but I'm going to augment the model every time I sample a new cluster. Yesterday, we said every new cluster is a new Gaussian sample from the prior. Now, every cluster is let's say again, a Gaussian, but I'm going to also sample a set of attributes. And in this particular model, what they assume is that the model is all the genes are Gaussian with 0 mean and large variance, and then they sample a few attributes that have different means that are off from 0 by some random amount. And all these are parameters that are estimated from the model. So it's just a variation on the Dirichlet process mixture. And then it's estimated by MCMC, the same algorithm as before, just with more parameters. And the paper is by Peter Hoff, my colleague. Okay. The third approach is extremely interesting, and I've been asked about it, but still all I have is this bullet. It's multivariate information bottleneck and multivariate information bottleneck. So this is an approach that covers much more than clustering. And it is also a fully probabilistic approach. It assumes that there is a joint distribution between the various variables. And the various variables would be the rows, the patients, the columns, the features, and then the hidden variable that tells me what clustering I'm in. Moreover, when it's called multivariate, it means that I can assume some structure inside these hidden variables or about these variables. And I'm going to just give you the idea of information bottleneck. If you want to read something interesting and new and like information theory, go and read the original paper and this paper. So there is an information bottleneck paper that's really good, and the multivariate information bottleneck paper that's also really good, and adds. It's a new thing. It's not boring after you read the first one. So the easiest to describe information bottleneck is for prediction. So forget about clustering for a moment. Suppose you have X, and you want to predict Y. And think of X as having lots of features. Some are relevant, some are not. How do you best predict Y? Well, they're saying the following. Let's think of a variable X prime and try to put X prime between X and Y, so that now X prime predicts Y, and X prime is derived from X. And I put arrows here, but they are derived probabilistically, so there are distributions between these. So instead of doing some direct prediction, I'm going to go through this. And what I want to do is as follows. The principle is as this. I want to find this, and this is my model, because this is given and this is wanted. Or if I'm in supervised framework, I get some labels for it. Yes? But this is my model. This is the creative part that comes in. And my model says that I want to have X, this is the information between X prime and Y. I want this to be high so that X prime predicts Y well. However, of course, X predicts Y well, only I don't know how. So the smart thing is that I want X prime to extract as little information from X as possible, so that I only get relevant information. So I'm going to put minus some lambda parameter, information between X and X prime. And X prime is the bottleneck. So I want to go from X to Y, but I want to get only the relevant information in predicting Y. Yes? And because it's formulated in terms of mutual informations, and we saw that mutual informations are related to conditional entropies and conditional probabilities, there is a training algorithm that is expressed in conditional probabilities. And if you're familiar with information theory as it's taught in in communications, in coding. So information theory in its sort of strongest original form is taught in transmission of information, like the Shannon limit and the channel capacities and all that. They are defined in terms of mutual information. In machine learning, we learn a little bit of it, and it's very useful. Like that little bit gives you a very good vision of what's happening. Okay, so there are algorithms for training to local optima this model. It's also a form of alternate projection. Okay, so this is information bottleneck. Okay, and so this is subspace clustering. please ask questions because every slide is a new topic, so don't wait if you do have questions to ask. All right, another topic. I have even less to say about this one. But it's a topic that's actually growing. And in fact, there are lots of places where you can think of it as being useful. And one reason I have so little to say about it is that I barely started reading it. And I barely started to hear talks about it, but more is to come. So think of it as an interesting area of research. Suppose you have a giant graph like the web, or the set of users. So maybe it's no point in clustering it because there are so many small clusters that you don't even want to keep them all around. Maybe you want, when somebody gives you a point, a user or a node or so, to see, OK, what's the local group of this node? So think of people. I'm the sample. What's my circle of friends? And if you think of people having a limited number of friends, you can see that this is not really a clustering problem, because in a clustering problem, you assume that the number of clusters is not larger than square root of n. So grows slowly with respect to n. Here, the number of clusters could be proportional to n or could be proportional to square root of n because everybody has a limited number of friends. So even with overlap, it's going to be pretty much linear. Yeah? The diameter of the graph can be small, but the number of clusters could be large, and it could be overlapping as well, possibly. How do I do that? And of course, I want to do it fast. And I have a very large graph, let's say. Well, there is this method, nibble, and I give you this method in its skeleton form. But this method was, OK, no reference for this either. The author is Daniel Spielman. And so they are theoretical computer scientists. And they invented this algorithm not for finding the local cluster, but for proving a new bound on the sparsest cut. How many of you know about sparsest cut and conductance in a graph? No, one. OK, so conductance in a graph is something extremely close. It's almost the same. So conductance has various definitions, and one of them is a normalized cut. But you break the graph into two only. And there are others that are close by. And there is interest in the computer science, in the theoretical computer science community, to bound these values for very large graphs in various ways. And this algorithm originated in a paper on a new bound for, and a new efficient algorithm for finding a sparse cut in a large graph as a subroutine. But it has been used by the same author again and again because it's a very useful little algorithm. And that says as follows. Basically, it says do a random walk on the graph, but leak some mass. So don't propagate too far. That's what it says. So basically, it says start with my node I. This is me. And to find my circle of friends, assume that you have already the connectivity, the transition matrix, and propagate starting from P, which is the identity vector, a vector that has an indicator vector, has 1 for me, for point I, and 0 for everybody else. And if I multiply it with the transition matrix of a graph, I get the distribution of at the next step. And if I multiply it repeatedly, that's the propagating the Markov chain, yes? And so if you multiply it again, you'll find the nodes that can be reached in 2 steps, 3 steps, and so on, with their respective probability of getting there, if this is a transition matrix. So this algorithm simply says propagate for t steps, where t is calculated carefully, and there are some proofs about what t you need for what purpose, to obtain what bounds. But that's not that interesting. The algorithm is interesting. OK, but it's not doing quite that. It says at every step, if I find that I can get somewhere only with low probability below epsilon, I delete that path at all. So every path that at some point has low probability is deleted. It's truncated. Yeah. And I propagate for t steps. And then I output all the nodes that I can reach. So these are nodes that can be reached with with reasonable probability. And that's a definition for the local cluster. OK, number one, this is reasonable. Number two, if the graph is sparse, it's fast, because you can easily see that you don't have to keep the zeros around. So you can implement this fast with local propagation only. And number three, if you read the paper or several of the papers that use it, it comes with proofs. The proofs are not immediately useful because they come in also, they're extremely, like this paper defines half a page of constants, literally. I should have shown it before it actually states the theorem about this little algorithm. OK, and the epsilon and t are defined there in sort of long formulas that involve those constants. However, it is usable, and you can prove things about it. Or things are proved about it, and you can use them to prove more other interesting things that are interesting for you in particular. OK, this is nibble. All right, so here is where the slides stop. I want to say a few words about ensembles of clusterings. What is that? How many of you know what ensembles of clusterings are? OK, some of you have heard of it. You guys are so informed. That's fantastic. OK, so suppose I am a person. I have a data set. I try several algorithms. I get clusterings. I try multiple initialization. I get a lot of clusterings. I know that this is a stochastic process, so I do some perturbations of the data set. I get more clusterings. I get a lot of clusterings, and or about I throw away the bad ones. I have 20 good clusterings. What do I do with them? Of course, you can go to the cluster validation section and see, can I do something there? Find the best by some other criterion. But there is another thing that you can do, which is to say, maybe they all reflect the data in some way. Maybe I should pool the information. And this is what ensembles of clusterings is doing. Or clusterings or consensus clustering. So there are two things you can do. You can find the consensus. So take all the clusterings and pool the information somehow. Or you can take all the clusterings and find if they cluster. And of course, I spent 7 hours and 50 minutes telling you how hard it is to cluster vectors, points. Now you have to cluster clusterings. That's even harder. And of course, this is just the beginning, so all ingenuity is welcome. But there is a reason to cluster clusterings. And that is that a data set can support more than one clustering. And this is something to think about very carefully. For whether it's possible. But sometimes it could be. So for instance, there are two equally good local maxima of the likelihood. Do you have a question?
Sorry, I'm not very clear as to how clustering of clusterings is different from bottom-up hierarchical clustering.
Oh, because the clusterings are not hierarchical. So let's say you run EM with different initialization, or you perturb the data set a little. Then you get some clusters overlap, but maybe some don't. Like, for instance, one cluster is split in one, but is not split in the other. And then if you have a dozen clusters, then you have all these variations. And so one thing you could find from this is that basically no run of EM splits all the clusters correctly. But if you overlap them, you will see immediately that you have to have a few more clusters, and you get something that's better than everything. Better than everything that you found directly by EM. So that's one possibility. This is consensus clustering. You find that the thing that they all agree, may not be a clustering with k clusters, but a little more or a little less. Or you can force it to be the best clustering with k clusters. Or, for instance, there are two clusterings, so the data set is slightly ambiguous. And so you can partition it in two ways, and none of them is better than the other, but they are very different. And this can easily happen if you take different attributes here. You can see different patterns. But that can happen in some data sets too, in other conditions too. And then it may be that half of your EM runs have found one type of clustering and half have found another type of clustering. Then it's not a good idea to choose just one. It's better to do this clustering of clustering and see that there are actually two groups, and pick a representative from each group. Yeah. And ensembles can also mean you keep them all and then you deal with that later, like you're Bayesian in some sense. Keep all the distribution around and do something at the next step. The best reference for this is Strail and Gosh, JMLR, and the final version of the slides will have all this. So if you can wait for, but of course you shouldn't be waiting. If you can wait, then you'll see them by probably tomorrow or earlier, the references. And this is what's covered by consensus clustering and clusterings of clusterings. If the one question mark that I want to say is that if you think of clustering carefully, you have to think whether when it's possible to have two or more clustering supported by the data set and when not. And I'll give you two examples. Half an hour ago, you saw a theorem that said that all good clustering on for k-means, all good clusterings are the same. If the data set is well clustered, well separated, then there is only one good clustering there. Because all of them, they have to be close together. So you are going to find a single cluster. Okay? But it could still happen, and perhaps even for k-means, if you construct situations carefully, or if you play with your parameter carefully, that you have different scales where you look at the data. So you can have, can you see here? Clusters like this and clusters like this, but then inside, this would be hierarchical. And with vectors, this is, how to say? With vectors and good separation, if you look for separation, this is probably the only way that you can get different clustering. So going back to your answer, it has to be hierarchical sometimes. But with spectral clustering, that's not the case. Because you can have, at least not in theory. Why? Because you have n eigenvectors. And for any perfect clustering, you need only k of them. So there could be another k eigenvector somewhere else building another clustering. And I don't know of any result that has ruled this out. So with spectral clustering, you could have a hierarchical clustering. So some eigenvectors sort of give you a 2 partition, but if you look deeper, you can find a 4 or 5 partition. Or you could actually have 2 concurrent partitions on the data that are good. So interesting questions there too. And with this, I'm going to stop. We are 5 minutes ahead of time, so if you have questions about anything, you can ask them now. Or you can ask them after I turn the microphone off. It's the same for me. Yes? Oh, thank you. And I must say, you deserve applause too, because you are a great audience. The best I've had for this course, actually. OK, now there is a question. Yeah.
Basically, if we have high-dimensional data in general, then how do we know what cluster will be MLSS?
So if we are in high dimensions, then how do we know?
How do we know each cluster in general? It's hard to draw perhaps for like that.
So how do we visualize them?
Now visualize.
How do we? How do I know which type? OK, so he's asking, well, how do I know which type of cluster to do? Or like if they're Gaussian or not? Yeah. Oh, this is a very hard question. So some people will say this is prior information. So try to look. So this means look at other clusterings done by other people and see what they found. Another thing is try different models. So if you're doing model-based, you can try mixture of Gaussians, mixture of Laplace, So you can select not only between different Ks, but BIC, for instance, lets you select between different shapes of clusters. So try a mixture of Laplace, try a mixture of Gaussians, and then compare by BIC. Another thing that you can do, you can change EM so that it tries to fit, when you have a cluster, it tries to fit different models in the same time. So you can put, with care, a mixture of different things in the same EM model, so that you can have some clusters that are Gaussian, some clusters that aren't. Yeah. So you can, if you have some, but again, you can try 3, 4, 5 types of clusters. It's not exhaustive. Or another thing to do, and this should also be sort of is contained in the course, if you have time, do a non-parametric clustering and then try to fit something to the, see what you get. What are the most important clusters and how they look like? Yeah, good, excellent question, as I said. Okay, are there more questions? Yes, Savish.
So as a statistician, I find clustering as a very good alternative to traditional hypothesis testing based approaches of finding interesting features in your data. However, I mean, in clustering, there are also cases where you might find patterns in your data when it is just random data, right? And especially, I would assume that this would be a problem in high dimension. Do you have any recommendations on confirming if this is a good cluster or measure the quality of clusters?
So the question was, suppose that I haven't found any good clustering in the data, and it's high dimensional. How do I know it? Because I can't look at it. Okay, that's cluster validation. I hope you all agree. So I can look at the model fit. If you fit, if you're a statistician, you know that there are measures of fit. How much alike is this, what I have found, to a mixture of Gaussians? So for instance, are the clusters Gaussian? And there are tests for Gaussianity. Or you can do what I said in this course, do the gap statistics, so create some null hypothesis, and compare the costs you get, and cluster them and see what you get. So some things that you can do, basically when you want to create a null hypothesis, what you want is to preserve everything you can about the data except for the clustering. So you want to create an unclustered data that's as much alike as your data. And of course, this is a sort of an oxymoron. How do you do it since your data is clustered? So that sort of is the place for ingenuity. What you keep and what you don't keep. Only the thing you have to not forget is that you can't rescale the dimensions, because that changes that's something that is part of the clustering. So it preserves the data. Yeah. So these are some things that come to mind. Statistical tests or tests of quality. Like compare the cost you got to some cost that you know is bad. And if you are far away, if you are close to that, then it's a problem. If you are far from it, then you don't know how, then you don't have a good answer. You don't know how better you could get. Or yes, there is a possibility, find an upper bound or find a lower bound for the cost. For spectral clustering, you have one, for instance. So you can know how badly you're doing. Yes?
I have a question about, have you seen any work on the interplay between, say, dimensionality reduction, for example, Gaussian eigenmaps, diffusion maps, and clustering to deal with this high-dimensional data?
So interplay, so reducing the data, reducing the dimensionality first, and then clustering. Yes, and some of these things come from, so for instance, as I said, principal components is really good if you look for clustering, as long as the clusters are about round. As long as the clusters don't add dimension to the data, you can do principal components and still preserve the information that's relevant to clustering. What you're asking, Laplacian eigenmaps and so, Laplacian eigenmaps is embedding without, so it's spectral clustering without the clustering step. So it doesn't directly improve on spectral clustering. But if you had clustered data in many dimensions and you went through Laplacian eigenmaps, again, so that doesn't improve on clustering really. There is some other work that I have not read, but I've seen around about dimensionality reduction in clustering. But I can't tell you much about it because No, I haven't gone that direction. Okay. Okay, then my time is up. Thank you again.